and some here. But let me tell you about coherent states real quick, because it's so important for the Superfluid-Mott transition here and for a lot of other things. Let's consider a harmonic oscillator. Okay? So this now has nothing to do with moving atoms or so. This is not at all what I'm talking about, as you will see. So it's a total side step. Imagine a mass of a spring, it oscillates. So it has a certain position and momentum, and those two oscillate out of phase. Right? So you can actually write this oscillation in dimensionless parameters to make the formulas look simple, but this here, this is just the position in some units and the momentum in some units, and your Hamiltonian is then simply the position squared plus the momentum squared. Like one is the kinetic and one is the potential energy potential. That's the position and kinetic with momentum both squared with the harmonic potential. So in phase space, where this is position and this is momentum, you have a phasor that goes in a circle. Does it make sense? Like that, because it's 90 degrees of phase position in momentum, at one point you're at the maximal excursion, but no velocity, no momentum. And then you have maximum velocity, negative position, and negative, this negative velocity, negative position, positive velocity, positive position. Okay? So this is described by a phasor. We call it alpha. It's a complex number, and it's just the position plus I times the momentum. Okay. Now, what is the time evolution? ddt alpha is simply I omega alpha t. You can simply see that it's quite the same. This means the solution is just e to the I omega t, which is the space of rotation. Right? You multiply this complex number by a complex probably. Okay, you just rotate the phase of it. Okay? So this is the phase of my oscillation as a phasor. The length tells you the amplitude, and the phase tells you in what oscillation state you're in. Now, let's go to quantum. What changes? Well, now x and p are operators, okay? And the Hamiltonian can still be written in the same way, but now h, x, and p are operators. Okay? Well, we can introduce ladder operators. You've all seen this in quantum mechanics when you did the treatment of the harmonic oscillator. Let me just remind you, the motivation here as well, you find if you have a term a squared plus b squared, which reminds us here to the x squared plus p squared, you can, it's called expanded as a plus ib times a minus ib. And just as motivation, so we can actually write operators a as x plus ip, and a dagger is x minus ip. This is a and a dagger, and again, there's this. You can also express in our position and momentum in terms of these operators a and a dagger. They're tremendously useful operators. They're called ladder operators, and well, we'll see what they do in a minute. Let's just see first how we can rewrite the Hamiltonian. If you write a dagger a, and you just multiply it out, again, if you're not familiar with any of this, homework the next time, then you multiply it out, and you get the a dagger a is just 1/2 x squared plus p squared minus 1. So it just, this is exactly what we have in our Hamiltonian, hence we can write our Hamiltonian as h is h bar omega a dagger a plus 1/2. A dagger a. So what is a dagger a? A dagger a is actually equal to the number operator. This is let's see what that means. H is for omega. You can write it as a number operator plus 1/2. This number operator discounts or energy eigenstates, essentially. I didn't do this beta here, but what you find is that you have these energy eigenstates now. Pretty number with n. Okay. And the eigenvalue of the is just the how many excited states you have in a harmonic oscillator. So if you the harmonic oscillator has a discrete energy spectrum, and this is just n. For n equal 0, you get the ground state here, and n equal 1, n equal 2, n equal 3, and so on. If you are in a harmonic oscillator, this has to be Gauss, so these are the Hermitier polynomials here. What's important now is that what you find is what happens if you apply the operator to one of these energy eigenstates. If you apply a dagger to the nth energy eigenstate, then you get the n plus 1's energy eigenstate. And this is what they call ladder operators, because you go up 1 in the ladder, in your excitation ladder. If you're in the ground state initially, you end up in the first excited state. If you're in the first excited state, you end up in the second one, and so on. And the opposite for A. Okay? Yeah. Now, everyone knows this about harmonic oscillator. But what happens now? What's a classical harmonic oscillator do? We say, well, typically if you go from quantum to classical is we just go to high populations and so on, and then quantum doesn't play a role anymore. So what happens for a big pendulum? Even if you go to a very high energy eigenstate here, turns out that the expectation value of the position is still 0. Why is that? Because if you square this wave function, you see you have a long wiggly wave function, but it has maxima on both sides. Okay. Like even a big classical pendulum, if it's in the 1/1,000,000th energy eigenstate, will still be delocalized over the two positions. And it's an energy eigenstate. It will not change in time. It's just sitting there. So your big pendulum is just delocalized over the two turning points roughly, and somewhere in between as well, and nothing happens. That's certainly not what we see in the everyday world. So how can we get states that are, so these are highly non-classical states, all the energy eigenstates. So this is certainly not what we get for a classical oscillator. How can we see what we get for a classical oscillator? This is where the Coherent states or Hilbert states come in. The trick is, let's see if you find eigenstates of these ladder operators. Without any motivation, let's just see what we get if you do that. Okay. So if we apply A, right, so an eigenstate means A alpha equals alpha alpha. Alpha is the eigenvalue if we apply A to its eigenstate. Okay? So let's assume we have them already. If we have our eigenstate here, we can decompose it. Like in order to find it, let's assume we have it here, and let's decompose it into into the basis of the energy eigenstates. So we just use the unitarity here, the sum over all the projectors in the energy basis. And so these are our coefficients Cn then. So our state alpha can be written as a sum over different energy eigenstates. Okay. And what we also know is that the nth energy eigenstate can be written as the lowest energy eigenstate, the ground state, the harmonic oscillator, the ground state, but then you apply the ladder operator n times. If you apply it n times, then you end up with the nth energy eigenstate. So if you know this and you just plug this in here, then we quickly find these coefficients Cn here, And if you also take the normalization into here, and if you also take the normalization into account, then we find that we can write our alpha in this form. And you find this over and over again. So this is really, make sure you understand, if you don't know this, make sure you go through this derivation once before the next lecture. You can write this alpha as a sum over the energy eigenstates, and you just have this factor here, alpha to the power in the sum. Now, what does this mean? What is the state? So this is actually the interesting thing is if you now look at the energy expectation, at the expectations values for the position and the momentum, this can be simply written like this, and we find that the expectation value of the position is simply square root 2 times the real part of alpha. Alpha is a C number now, and it turns out that this alpha is the same alpha I was showing you before for the classical oscillator, my phasor for the rotation. Okay. The position is the real part of alpha. Okay. The momentum is the imaginary part of alpha. So if alpha is a complex number, that's what I was saying before in phase space, right? Position, positive momentum. So if it's purely real, then it's a certain position, purely imaginary. It has a certain velocity, a zero position. Okay. And if you look at the time evolution, this is also very simply calculated in 2 lines, and you find that this is exactly like the classical phasor. The phase up to time t is just e to the I omega t times alpha naught. Like if you start with alpha naught, that's let's say 1, then after a certain time you have to rotate this this 1. You have to multiply it by, well, after a quarter period you multiply it by I. So 1 turns into I, and then minus 1 and minus I, and so on. It just rotates, just like a classical phasor. And so we find, and you can do much more, you can look at fluctuations here, and so on. But you find that this is essentially what comes closest to a classical situation. If you are in one of these coherent or classical states, then everything behaves kind of like we expected from a classical oscillation. There's much more to be said, but for example, the fluctuations are interesting. The uncertainty of these states is always the same as the uncertainty of the ground state, the harmonic oscillator ground state. What actually happens is that you shift your, if let's say, this is our phase space, right? So this is real, this is the real part of alpha, which corresponds to the position. This is imaginary of alpha, which corresponds to the momentum. For the harmonic oscillator ground state, we are here, but we're not exactly here. We actually have the Heisenberg uncertainty. We have the same amount of uncertainty in position and momentum. Okay. And if we now have a classical oscillation, what happens is that we actually shift this. This is alpha. Now we shift this to a certain point here, and it will then oscillate like this, but we still have this uncertainty. This is also why 2 coherent states are not orthogonal, they are only quasi-orthogonal. Because nearby coherent states still have a finite overlap. So you always have this quantum uncertainty. In this context, it's easy to understand things like squeezing or the kind of things. If you deform this, you can independently deform your uncertainty. More. And okay, what does this have now to do with our system? So first of all, what Roy actually pointed out a long time ago, and we'll probably also talk about it, and I've talked some about already, is that don't have this slide now. Okay, let me just do it handy. So this is just the solution of a harmonic oscillator. Of course, there are lots of systems that you can approximate by a harmonic oscillator, and one of them is an electromagnetic field. Consider we have a standing wave in a cavity, okay? And you may know a standing wave in a cavity goes back between having all its energy in the electric field and then the magnetic field and the electric field and the magnetic field. They two are orthogonal to each other, but it oscillates back and forth between those two. And these two conjugate variables essentially now correspond to kinetic and potential energy in this harmonic oscillator. And that way, you can now describe a light field in a cavity with these coherent states. The basic idea is you get the same kind of ladder. In a harmonic oscillator, you get the energy eigenstates. How are the, what is the corresponding thing called in the cavity?
Modes.
No, this is for one mode. So, like one mode, the idea is that one mode can have an electromagnetic wave. That's where energy is oscillating back and forth between being in the electric field and the magnetic field. And so this one mode, what is this ladder of energy ladder? What does that correspond to?
Photon numbers.
You know. Photon number, exactly. This is photon number. I don't want to write out the Hamiltonian now, but you can see it's same Hamiltonian, and this now corresponds to photon number. If it's empty, I mean, you can still write it, yeah, actually h bar omega times n. This is the number operator plus 1/2. If you have no photon, you still have vacuum fluctuations, 1/2. Then you can have 1 photon, 2 photons, 3 photons. Okay. Now, if you have two cavities with 1 photon inside, and you let the photons out and let them interfere, do you get interference pattern? Or how would this look like? It's kind of ask for intuition for that, but so it turns out
you have to ask that question very carefully.
Exactly. We'll actually get interference pattern.
Yeah. You're going to average over a whole bunch of
exactly. So in the ensemble average, you will not see an interference pattern, and the reason is that if you think about a light field in a cavity, like normal, like laser light or something, in a cavity, this is actually a coherent state. And so this sum that I was writing in the last slide, this is actually, so this is the sum over different energy eigenstates with the Poissonian statistics actually fine. So the if you just do a diagram, sorry, I had a few more slides on this, but I don't have them now. You
Let me want to turn on the light.
Yeah, it's okay. Maybe it's a medium level. So if you have a cavity with a classical light field in it, then you will actually have a superposition of having no photon, 1 photon, 2, 1, 2, 3, 4, 5, 6, and so on. You will have a superposition of different photon numbers. You never know, unless you do enormous amount of tricks, you never know how many photons you have in the cavity. It's this, because you're really a superposition of different photon numbers. This superposition gives you this classical state. The most important classical state is that, the most important property of that is that you have a well-defined microscopic phase, and that's what the phase of a classical electromagnetic wave. If you have a standing wave in a cavity, you know the phase of the wave that's in there. You can couple the light out and measure it via interference. And this is exactly this expectation value of alpha, like expectation value of your field operator or the ladder operator here. Alpha is simply alpha. This phasor that I was talking about. This complex phasor. So this is good. So this is basically quantum optics. Based on this you can back to all this squeezing and so on. Now, we do the same with atoms. Okay, now Bose-Einstein condensate, I told you already, in the weakly interacting case, each atom is everywhere. But that means if you, so how many atoms do you then have on one lattice side? If each atom is delocalized over all the lattice sides, how many atoms do you then have on the single lattice sides? Let's say you have 100 lattice sides and 100 atoms. And each of the atoms is delocalized over all of the 100 lattice sides. What's your atom number on a single lattice side? Always one?
Depends on the interaction energy.
But if that's weak, or non-interacting?
And there's some fluctuations about the mean number.
Right, there are fluctuations there. That's exactly. So if you have 100 weakly interacting atoms on 100 lattice sides, you get exactly this coherent state. You get exactly this coherent state with an expectation value of 1, but Bosonian fluctuations around it. So this, sorry, I had it on the slide, but this will look roughly like you have a finite probability of having 0. Forgot how the height exactly is. I'll show you. I think they have the same height as and a tail. So this is the probability of having no atom, 1 atom, 2 atoms, 3 atoms. Okay, but it's really it's a coherent superposition of having no atom, 1 atom, 2 atoms, 3 atoms. And the trick is, it's not just any superposition, it's actually a superposition in a way that you can describe that such that you have a macroscopic phase. It's just like with light, photon number is arranged such that you have a classical electromagnetic wave. This is here saying the atom numbers are arranged such that you have the so-called macroscopic phase. And I will show you in a minute where this comes into play.
So why is atom number even a good way of describing what's going on at the lattice sites? If it's, it's not an eigenstate of atom number.
But it's an initial basis. It's an initial basis, right? Okay, I'll show you.
You can measure. And it's something.
Right, and something you can now measure. Exactly, with the quantum microscope. Until recently, you couldn't measure it, but now we can measure it. Okay, so just a little bit background. If anything of this you didn't know, look it up. And let's continue.
That's good.
Okay, so now our atoms in the lattice. We consider the weakly interacting case. Let's consider a strongly interacting case now. And so what can happen? This is our Hamiltonian now, because the atoms. Okay, what can atoms do in the lattice? You said earlier they can tunnel from one lattice side to the next. Okay. You always consider now atoms in the lowest band, so on each lattice side only the lowest vibration say that they can tunnel between lattice sides. What happens if 2 atoms come on the same side? The beauty is that our atoms have pure on-site interaction. They have this very, very good precision. An atom only interacts with an atom on the same lattice side. This is different from electric charge or so in traditional condensed matter. The amazing thing is that the interaction of the atoms, it's kind of like point-like interaction, but it's nothing stochastic. It's fully coherent. It's just, all that happens is that if you have 2 atoms, the energy is raised by a little bit. This little bit is U. So now these 2 things, we can understand this. First of all, the atoms can hop. Okay, this is our field operator, our bosonic field operator. So this is just like the A I was using in the coherent state analysis, but now we need the index here because we have lattice sides, okay? So the atoms can hop from one lattice side to the next. This means that you create one on side I and you destroy one on side J. Okay, that means you hop from one lattice side to the next. So if you know this, these ladder operators, this creation and annihilation operators or field operators, we now understand what this means. Okay, this is hopping from one side to the next. They can only hop between neighboring sides. The second part is they can interact, and well, if you have n atoms, then n atoms, you have to be careful to not double count. So n atoms interact with n minus 1 other atoms on the same lattice side. Okay? Clear? Any question? So these are the two things. Experimentally, we can wildly tune the ratio between this tunneling and this interaction. We do this mostly by changing the depth of the lattice potential. If it's shallow, they can tunnel very quickly. If it's deep, then they hardly tunnel at all. So let's consider, again, this weakly interacting limit where the tunneling is dominant and the interaction is weak. What is our ground state now? I was telling you already, just claiming our ground state is every atom everywhere. This is exactly what this says here. The ground state is one atom is the sum of being created on all of the lattice sides, in either of the lattice sides. Right? So this atom 1 is everywhere to the power of n, where n is our capital N is our atom numbers, our microscopic wave function. But this doesn't help us much. It's much more intuitive to think about this picture now in the coherent states. So this was our coherent state earlier. So on the single lattice side, now I was at the index I of the lattice side. On the single lattice side, what we actually have is coherent superposition of different atom numbers. Just like you have in a cavity, different superposition of different photon numbers. And just like you have in a classical pendulum, a superposition of different energy eigenstates of the harmonic oscillator. Okay, well, I have to be careful because we're not talking about the motion of the atoms here. So, superposition of different atom numbers, okay? But in a way such that the expectation value of this field operator is equal to, okay, here I didn't call it, think about this being alpha I, okay? The expectation value of my field operator is just alpha. And if I have I lattice side, then this value and index I here, okay? Okay, so I really have a coherent superposition of all these possibilities. No 1, 2, 3. Now this finite expectation value, this is what gives rise to this multi-matter wave interference pattern. If I look at, after a long time of light expansion, the phase of all these waves, the matter waves that interfere to show me these interference pictures, those are exactly these coherent states described by these phasors. So if they're all the same phase, like all a similar length, but what's important, all the same direction, then I see this beautiful difference pattern. Okay. Now, but if it actually turns out this microscopic phase and the atom numbers are also conjugate. So that means that if my microscopic phase is well defined, my atom number so if your microscopic phase is known, then your atom number is maximally uncertain, and this is exactly just reflected by this coherent state. Let's see, one more thing. You can actually, maybe do one more thing with that weakly interacting. You can actually nicely see now, if you know our Hamiltonian here, if you look at the first part, then we can actually understand. So we understand this hopping part in a particle basis, right? Like one atom hops to the next side. We created in one and destroyed in the other one. But we can now also, if you know that we have this weakly interacting regime, if we know that it's valid to replace the expectation value of that with a C number, then we can actually exchange the operator with a C number. So the term minus J times AI, they got AJ, actually turns, we can replace this with the expectation value of the field number, is minus J alpha I convex conjugate, like this phasor on the I's and J's lattice side of the Markus, or the expectation value of the field operator, right? And if you think about what that now means, the product of two vectors, well, the product of two vectors is the cosine of the angle between the two vectors, like the product of the two complex numbers, this is the proportional to minus j times the cosine of phi I minus j minus phi I. So this is alpha I. This is alpha j. This angle in between here is by j minus by I. Okay. Yeah, times square root ni and j, because the length of alpha is given by the square root of the atom number. What this now tells us, why is it energetically favorable to have this coherent state. Well, if you have a number state on this side, then this is 0. If you have this coherent state, then you have a term that's proportional to cosine phi j phi I. And so if the phase is the same here, then this is maximum. So if you have the same phase everywhere, you can lower your kinetic energy by j. It's just like in a Josephson junction or so. If the phase is, if you have a situation where you can define a macroscopic phase on a lattice side, that allows you to lower the total kinetic energy exactly by j. And if you go to the band edge, as I was showing you earlier, where the phases are opposite, then this cosine changes sign, and you have now raised your kinetic energy by j. And so this means that actually the band structure, even in a many-body picture, you can understand as this. You can lower it here by j, and here it's raised by j. You see that immediately. I hope I didn't mess up numerical factors, but that's correct. Okay, so that's an intuitive way to understand that. Let's continue. What happens now if you have strong interactions? Well, it's easy to see. If the atoms strongly repel each other, these fluctuations in atom number become energetically very costly. You don't want that, right? Think about it. If you have one atom on average, and the atoms strongly repel each other, what do you want? What's the state of lowest energy then? If the interaction is dominant, well, exactly one atom, right? Because if you have a 0 somewhere, then you need another lattice side with 2, and that raises the energy a lot, by the attraction energy. So these fluctuations that allowed you to create the coherent state that lowered the kinetic energy before, that now becomes energetically costly if you have strong repulsion. And that's what happens then. So if we increase the role of the interactions, then we get into this regime where we have a Mott, a so-called Mott insulator. In this case, for example, one atom everywhere exactly. But now the atom number is known, and the conjugate macroscopic phase now has to be maximally uncertain. So, so the interference peaks actually will disappear. I don't think I have time. One can understand it in a double well picture. If you want to look into this, you can look into Lattice, for example. This is an alternative way, not thinking about coherent state, but just two atoms in a double well give you a nice way to understand what's going on too. Okay, so when we did this in the experiment, we raised the lattice potential. We saw that this nice multiple matter-wave interference pattern vanished, and all the coherence was lost. And so we assumed back in 2001 that we created a Mott insulator state here, because we could also see we could regain the coherence and so on. So something must have happened that's reversible and that gets rid of all the coherence. And so what really happened here is that slowly, or what we assumed was that the coherent state was turned into a number state continuously. And in the condensed matter language, this is going from a superfluid to a Mott insulator. The nice thing is that now with the quantum glass microscope, we can directly look into this. So let's have a look. In the superfluid, where each atom is spread out everywhere, we expect this Poissonian number fluctuations corresponding to the coherent state. And this is what we get in our microscope. This is a little blow up of an area where we have a superfluid. Okay? And I told you that we measure the parity. So for Poissonian fluctuations, you would expect to have even and odd population about as likely, and that's exactly what we see here. So it's just as likely to have odd or even if strong fluctuations in the atom number.
In the previous slide, can we think of intermediate states as squeeze states, for instance?
As squeeze states, exactly. So it's really squeezing. It's identical to what you have in quantum optics. You squeeze a coherent state. But the nice thing is that with our atoms, we can actually have strong interactions. With photons, that's incredibly hard. So our squeezing can be much better, much bigger than what you get with photons. So we have the extreme case here that we can continuously squeeze all the way to a very pure number state. And that's what we do. That's in quantum optics language. And that's what we do here. Excellent. Yeah. Is there a question? And right. And for the Mott insulator, we expect one atom per site everywhere. And now we can probe, and we see we really get this with fidelities of about 90, up to 99% by now. We get exactly one atom per lattice site. Okay. And so this means we really have created a number state. We have gone from a coherent state to a number state here. And we can go back and forth and really image this locally now. But keep in mind, these are not classical fluctuations. This interference pattern show you that this is really this kind of microscopic phase, right? And we can continuously, we can measure the squeezing parameter here or the probability of odd population and compare this to state-of-the-art theories, essentially, and find indeed the squeezing from Superfluid-Mott insulator with a quantum gas microscope. If you have studied the Mott insulator in condensed matter, then you know there's a Mott lobe structure here. Depending on the chemical potential, you have areas in this space where the chemical potential and the interaction strength, where you have exactly one atom, exactly two atoms, exactly three atoms. And in our homogeneous system, in the trap, we actually simultaneously have areas with right, so we actually get a shell structure because this chemical potential here corresponds to a situation where in the middle of the trap we have the highest chemical potential. I'll show you the slide next time. This is also done. This is nicely shown. So we get let's just look at it intuitively. So these are the pictures again. If we just put a few atoms into the trap, then we will get a Mott insulator in the middle. If we but what we also have then in the experiment is this overall harmonic confinement. So as we add more and more atoms, the atoms will form a larger and larger Mott insulator region. But ultimately, it's energetically favorable to put another atom in the middle and start a new shell of Mott insulator with two atoms per side. And as we add more and more atoms, we get this shell structure. Let me remind you, we are measuring the parity. So here we have 0 atoms, 1 atom per side, 2 atoms per side, 3 atoms per side, so on. Up to 4 atoms per side in the center here. 1, 2, 3, 4 atoms per side. And so the nice thing is with the microscope, we can image this directly. These are ensemble averages. That's why I have grayscales. In each of the pictures, we get a single realization where we can tell exactly the population on each side. Okay. And this is then the average. You can nicely see this shell structure. And keep in mind, we start with a coherent state here, with the superfluid state, and then this extreme squeezing occurs, and we get the number states. And also, just to mention, so this is a quantum phase transition. This kind of phase transition from superfluid to Mott insulator also happens at absolute zero temperature, where all the thermal fluctuations are frozen out. This is probably a good time to end anyways, right?
Okay.
Perfect. Then I will continue here in the next time. Thank you.
Thank you so much.
But actually really hard to understand, or even impossible so far to understand these materials and even these effects from first principles. On the other hand, there is theoretical condensed matter physics, where you try to come up with a simple model to understand that. But these models are much simpler, and even these models are hard to calculate theoretically, and you cannot test them. You don't know. Have you made the right approximations? Have you done the right thing to understand them? With our optical apps, as you will see, we actually can realize some of these models now that are relevant, for example, to condensed matter physics. And so the hope is that we really have kind of like a quantum Lego, where we can put together a quantum system piece by piece, and you have full control over the system. You really know it from first principles. You can observe individual particles. We really have a good handle on that. And so the hope is to really increase understanding here. I should mention that with fermionic atoms, there are already the first examples now where you can really use atoms to answer questions in condensed matter physics. Markus Greiner will be telling you about this later this week. How if you without lattice, just fermionic atoms in a cloud, how you stand precision measurements to really find out which of the theories are correct, which of the approximations are valid, which ones might not be, and so on. So this is really starting now. With optical lattices, we are also approaching these kind of possibilities. Okay, so I will be telling you about, in this sense, we call this quantum simulation. You have some Hamiltonian that's of interest, for example, for condensed matter. You put it together using optical atoms. And I will tell you a little bit how we can do this. So at first we have to start code, as Bill Phillips was already showing you, but let me also show, since you're experimentalist, I can show you a movie of a cloud of cold atoms here. It appears white, it's not really white. In reality, it's infrared, but the camera sees infrared as all colors, and so it appears as white. And you see a mod that is switched off. And here we detune the mod, the magneto-optical track is unstable. But in particular now, you can see when we switch off the mod and have the lattice, you can see how slowly the atoms fly apart. And you have to contrast this with, at room temperature, atoms fly with about the speed of sound, right? So this is the laser cooling that Bill was describing. Essentially, this leads to these kind of systems, and it's nice to see here. Bill also mentioned. Go ahead.
Was that video in real time? Or
yes, that was real time.
which atoms are those?
Rubidium, and they have a position in the infrared 780 nanometers, and that is it. So Bill already mentioned how cold it is, but let me also give you a take on this. So this is room temperature on the logarithmic scale here in electron volt in Kelvin.
What's the lowest density you can preserve? What's the lowest density?
The lowest or highest possible. The atom cloud. So in the beginning, the density isn't that high. So in the end, you have about like 5 atoms per cubic micron or so. That's how I usually think, because I think lattice is 1 atom per lattice site. In the beginning, it's much less dense, orders of magnitude less dense. So other people would still call this a vacuum, but we call it cold atoms. Okay, so this is room temperature. Then you can get really cold, right, with liquid nitrogen or even liquid helium, and then you're here. We are much colder. In our recent experiment, we have temperatures of tens of picokelvin in the magnetism that I will be telling you about next time. And we think about this is about as cold as the LHC is hot. It's as we start at room temperature. It's as many orders of magnitude colder than you go up. You get to the highest temperatures you can make in the lab, but their lab is a little bit larger than our lab. Okay, and yeah, Bill was telling you, you start with a thermal sample, then you found a Bose-Einstein condensate one. So one way to think of this, kind of like in atom optics, is if you have a hot or warm or pretty cold gas of atoms, each atom is like a little wave packet, and as you then cool, as soon as its wave packets start to overlap, they want to populate one gigantic wave packet, and that's your Bose-Einstein condensate. And in the end, you have nearly all of the atoms in this one big macroscopic metal. That's what I checked. Again, like I also mentioned, I will come back to that analogy later. It's actually like with photons. Photons in a laser. You have this, a standing wave, and you have a lot of photons in the same standing wave, very macroscopically populated. Here's the same, a lot of atoms in the same harmonic oscillator level. Or if you have interaction that changes a little bit, but let's just leave it at that for now. So there have been many exciting experiments after the first BSc has been reached in '95, Agila and also at MIT and other places. And the beauty is that it's actually simple. It's simple, very simple quantum mechanics, nearly classical in a way, in a classical way. And all the atoms are described by one collective macroscopic matter wave. It's just like a single particle wave function, except you just scale it by the atom number squared and But pretty much, if you know single particle quantum mechanics, you can understand a lot of these things. And the interactions, and the many-body physics enters as a mean field, as an effective changing of your potential landscape due to the presence of the other atoms. Again, I don't want to go into detail here, but and so the superfluid, you can get all the superfluid effects like vortices and so on. They have these beautiful experiments. But of course, the condensed matter theorists, at first they were a little bit condescending actually, because they said, well, this is the theory around the 50s and 60s, it's actually very simple. It corresponds to a very simple model in condensed matter physics, where each atom is inspired by this macroscopic wave. What condensed matter physics is talking about is strongly correlated physics, where interactions are important, correlations between particles. One particle is entanglement, all these kind of like real quantum features, essentially. And so, of course, the field wanted to move in that direction to address these things. There are different possibilities to do this. One is really crank up interaction. And so Carl Weinman at Agila, they did that with the so-called Feshbach resonance, strongly interacting BC, and indeed they saw interesting physics. Unfortunately, what mostly happened is that the whole thing exploded because of the strong interaction, but that was kind of an example where you use strongly correlated physics, and soon they also saw like molecule formation and things like that. Essentially, your interaction energy has to be comparable or larger than the kinetic energy. Again, one way is crank up interaction. Obviously, that at some point interaction energy will be larger than kinetic energy. But there are other possibilities to do this, and we are using optical lattices to do that. The trick there is that in a lattice, you change. One way to think of this is through the presence of the lattice, you change your effective mass of the particles. And with that, you actually change your kinetic energy, because the mass it scales with the mass. That's one way to think about it. And so with that, we can enter the strong correlated regime. So I will tell you, like in the main part of the talk, this will be the topic, and I will try to formulate a little bit more in quantum optics kind of language. Okay. Well, and the basic idea then is that with these optical lattices, so this means that we put the atoms essentially into a periodic potential landscape. You can think of it like an egg carton, like balls in an egg carton, but we have quantum eggs. And the analogy, you can immediately see what the analogy is to like a real material. In a real material that you can hold in your hand, the properties are given, or the electronic properties, and that's what this analogy is about. The electronic properties, like in a superconductor or so, comes along because you have the gas of electron, the degenerate gas of electron, moving in the periodic potential landscape given by the ions. So you have the ion in the crystal and the electron gas that lives in that potential landscape. We now have this analogy where now our atoms actually play the part of the electrons or the Cooper pairs. And our periodic potential landscape is not given by these electric charge signs, but instead by an optical light field, periodic, like a standing wave. I'll come back to that later. So before I tell you about that, let me just mention other fields, and some of that you will see in other talks, and some things are beyond the scope of this winter school. But so the other way to get into strongly correlated physics is with fermions. They've been able to create generalized Cooper pairs of these fermions if you create strong interaction. So this is quite fascinating. But Markus Greiner will be telling more about this, and he also showed some recent really quantitative results that can really benchmark theories now. And the natural extension is to put fermions in lattices, then you really have a system like electrons in a crystal, and again, the goal is then to see Cooper pairing. And the interesting thing is that if you just have a simple lattice and you put electrons in there at cold enough temperatures, you actually should have something that is quite similar to what you get in a high temperature superconductor, and then you get D-wave pairing in Cooper pairs in the system. So this is one of the big goals in our field right now. There's a lot of work in that direction. And yet a different field, and in the next lecture I will tell you a little bit about that, is quantum magnetism, where you don't just have particles hopping around like condensed matter. A person would say like the charge degree of freedom. We don't have charge atoms, but we might still call it that way. Instead, we worry about the spin degree of freedom, meaning we somehow create a spin. An atom somehow has a spin. This can be an internal state, but the spin can also be encoded in the external degrees of freedom. Okay, so we'll come back to that next time, but let's go back to the basics. So we want to create an optical lattice, a periodic potential landscape for light. How do we do this? Well, first of all, we can trap atoms in light. It's simple. So here, in contrast to what Will was telling you about, we have very finely tuned light. So there are no spontaneous processes. The atom will never go into the excited state. Instead, we just wiggle a little bit at the electron cloud. And we do this in a way, imagine you place an atom into an electric field, you will induce an electric dipole. This induced electric dipole will now interact with the external electric field to give you a potential. We don't have static electric fields, we have finely tuned light, which is like a quickly changing electric field, but it doesn't really matter. All you have to do is average over one cycle of the oscillation, and then we get the net effect. And so at the end of the day, you just get a potential that is proportional to the light intensity, and then depending on whether we're redly tuned or blue tuned, this induced dipole will be in phase or out of phase with your driving light field, and hence you will either get an attractive force or a repulsive force. Either of those can be used for trapping atoms. So lattices. How do we make lattices? Well, we can simply interfere to laser beams, and as you know, if you interfere to beams, you get an intensity pattern. The polarization is not loud enough, and so we then can create a lattice, well, basically the lattice size is half of the wavelength. With 1D, 2D, 3D, right? At the end of the day, we can have lattices in such a system. And that's what we do. We create these potentials, and we then load a Bose-Einstein condensate into these potentials, and we can get a situation where we have up to a few atoms per lattice site, for example, and can do experiments with it. It's actually quite amazing. The BEC is really split up over all lattice sites.
People try going beyond sinusoidal potentials, for instance, using higher harmonics and simulating more realistic or mass matter potentials, for instance.
So usually most of the experiments are in a tight binding kind of situation, as we will see in a moment. where the additional vibrational states don't play a role, and that would mean that the exact shape of the potential doesn't play a role. What does play a role is the band structure overall. So for example, there are recent experiments, we don't use a square or a cubic lattice, instead you use a hexagonal lattice, like graphene, and then you get a Dirac point, for example. So just recently, this is only about to appear in nature, is like the graphene lattice, and they saw the Dirac point, where you have a linear dispersion in Dirac fermions, essentially. And these are very promising directions, actually. Or another way is that you make double well, for example. So you can certainly make more complicated lattice structures there.
How would you put a DC in an optical lattice? Would you first just make a dipole trap and then somehow make the lattice?
Exactly. I will show you how we do it in our specific experiment in general, and the first experiment that we did in 2001, what we did was just create Bose-Einstein condensate in a magnetic trap, and then superimpose the lattice, but slowly ramp it up. So just like you don't put the BEC into the lattice, you put the lattice into the BEC.
Right. Okay, so
It just splits up, but it's actually it's pretty mind-boggling, right? I mean, you get used to in a BEC, every atom is described by a macroscopic wave function. What does this mean now? Like in this lattice, for example, this means that each atom is everywhere. Each atom is in each of the lattice sites. That's if you want to write the many-body state, that's how you would write it. One atom is in superposition of all the lattice sites to the power of n. We'll come back to that. Okay, just to show you that actually this is not just possible with atoms to use light. People use this optical tweezers. This is an old movie from Ted Henge actually, where he used laser beams. You see two interfering laser beams, like a 1D and a 2D lattice, and now he puts just in water polystyrene spheres. Okay, and here the spheres just illuminated. You can see it better on this screen, by the way. And then you see how they get attracted by the light maxima. So this is nothing specific to atoms. It's just, in this case, you can understand it as index of refraction. We can talk about it later if you want to understand how this works. But actually, you can also understand it. The light polarizes your medium, and that interacts with the light again. And so that creates an attractive potential. See how they're helping? In 94 already. With just little polystyrene spheres. Okay, so let's stay in this weakly interacting regime for now, where we forget about interaction, basically, and just have this Bose-Einstein condensate in the lattice. So, if our lattice gets reasonably deep, we say we're in the tight binding, each lattice site then might have multiple bound states, and you can think of this like a harmonic oscillator. Okay? Each lattice site is a bit like a harmonic oscillator, with bound states that are allocating the lowest or the highest. Usually, you always work, or if you just load the BEC into such a lattice, you automatically end up with atoms only in the lowest band. Okay? That's like, because we have cold atoms. So they're all in the lowest vibrational state if we treat this locally as a harmonic oscillator. And in a very deep lattice, this is exactly a harmonic oscillator. Okay? Infinitely deep lattice. What happens if it's not infinitely deep? What could the atoms do? Form bands, but what? And what does it mean? What would an atom do then that you place into this lattice site? Right, they can tunnel to a neighboring site, or in other words, the wave functions spread out over multiple sites. Exactly. Okay, but so let's just consider this kind of BEC. You can think of it. You have a little Bose-Einstein condensate on each of the lattice sites here. And they are connected via tunneling, essentially, and you can just describe it like this, essentially. Your Bose-Einstein condensate is just split up. So the whole thing is still like a single particle wave function, but now you have the sum of all the lattice sites. Like each of the atoms is in the sum of these little localized wave functions, called Barnier wave function in the lattice. If you have that, how can we prove that we have that? How can we see that we have that? What's so beautiful about these microscopic matter waves is that we can probe them with interference. So this microscopic wave functions just like light. Okay. BC, you have all the atoms in a single, described by a single microscopic matter wave. It's just like in optics, all the photons are in the same mode. You have a classical electromagnetic wave where all the photons are described by the same wave, essentially. Okay? How can you probe that? You can probe it by coherence. If you shine light onto a multi-slit pattern, and afterwards you have a spherical wave emitted from each slit, let's say, they all interfere and give you an interference pattern. We can do the same with the atoms. So keep in mind the interference pattern I will show you is not light interference, it's atom matter wave interference. Okay? The basic idea is, so here, this is a simulation. This is a small Bose-Einstein condensate loaded into the lattice with only quite a few lattice sites in this case. In reality, we have about 100 times more lattice sites typically. And if we now trap them, what would happen if we switch off the lattice potential? To the atoms on one side, let's say. Like imagine you have a matter wave that's confined to a tight potential. This has a shape of a small Gauss. What happens if you now switch off this potential? It spreads, exactly. This is way too tight. So this Gauss will just spread and get bigger, bigger, bigger. So you have an expanding matter wave, but this will happen for all of the lattice sites now. Okay, they spread out and interfere and form a multiple matter interference pattern. This is a simulation how this looks like. The color shows you the phase. Okay, so initially it's the same everywhere, and then as they expand, they form this discrete. So you get one blob here that has the overall shape of the original condensate, and then you have one blob here that moves down, hence the phase gradient down, over, up, diagonally. Okay, does it make sense? So this is, and you can do this with the atoms. So here the atoms are in the lattice. As you switch off, you have a coherent matter wave emitted from each lattice side, and they form a multiple matter wave interference pattern, like you see here. You get this beautiful, very narrow peak. So essentially, the atoms. If you want to say it that way, the atoms cancel each other, the matter waves cancel out each other everywhere except at these discrete locations here. And with that, we can show that we have a macroscopic matter wave in a lattice via this interference. So it's kind of like with light. Maybe I could mention this here for the first time. Imagine you have an array of cavities. They give lattice and trap atoms, trap a matter wave. It's the same as if you could have an array of little cavities that all trap light. But they're all coupled to each other. So the light everywhere oscillates in unison, like it's all in sync. And if you now open all the cavities all of a sudden, then you also see a pattern like that. Of course, with cavities, it's hardly possible to do this because you can't hold on to photons that far. There are actually some experiments that go in that direction. Okay, but here, yeah, we do it with atoms. We have a 3D lattice typically. Actually, later I will tell you about 2D or using 2D experiments. Right, so this is 3D, and then we can actually take a picture. So the picture I was showing you is we let the atoms expand, and then we do a shadow image. We illuminate this with resonant light, and they cast the shadow into our light beam, and we get a picture like this with a normal camera. This is how we take the pictures. Now, there is a band structure. So we said we have. Let's just talk about single particle physics for now, because we also said that our BEC behaves like a single particle more or less. What does this band structure mean? How would you expect the energy might, let's see, if you have just lattice sites with little BEC everywhere, and there's tunnel coupling, can you have a net flow of particles in that situation? What would you need for that? So you would have to accelerate it first, but what does that now mean? A state of a particle in a lattice that moves with finite momentum. What happens to the phases between lattice sites? So at rest, the phases are the same everywhere. And that's when we get this beautiful symmetric interference pattern. What happens if you now apply a gradient? You actually get a phase gradient. Okay? So, and the energy of that, the kinetic energy, this is given in the lowest, like if you look at the lowest band of the lattice, this looks sinusoidal. It's very weak here, but this is really sinusoidal. So in the lowest band, we would get a situation like this, okay? If the lowest energy of the phase is the same everywhere, we have and here at the edge of the Brillouin zone, okay, here the phases are the same everywhere. Let's say 0, 0, 0 on the other side, like this. And as we go here, we start to get a phase gradient. For example, like 0, let's say pi half, and pi, and so on. Okay? And here at the band edge, we have 0, pi, 0. So we always have opposite phases. Okay? And this is the highest energy state. If you have opposite phases, you might know this from Josephson junctions. But the phases are opposite, then you have, that's the highest energy and cost of energy. They're the same in the game. And of course, this is the same as this again. So if you accelerate more and more and more, it's 0 pi is the same as here. So the Bragg reflection end up here again in 14 years. At another time, there were beautiful experiments showing these kind of things also by Bill Phillips' book, for example, earlier on. But I don't want to go into details here, just to kind of make a little bit intuitive what these band structures mean. This is in the lowest band, it's a symbol. The next higher band, well, it's the same story, except now you, on a single lattice side, you're not in the ground state, but you have a wave function that has a zero crossing. Just like the next harmonic oscillator state. So for this, but if you really want to do it, this is kind of matter physics, essentially, the band structure. We can show this band structure, actually, if you start with the Bose-Einstein condensate, we're just in the middle here, but if you then shake it and do nasty stuff to it, it decoheres. And the dynamical instabilities, and we can populate the entire Brillouin zone equally, okay, just incoherently. Atoms are spread out over this whole band. And if you do this, we get beautiful pictures. Because you can map this by switching off the lattice, which was pioneered actually also by Ben Phillips' book. If you ramp down the lattice, you populate the whole band, but only the lowest band. If you now map it, if you switch off the lattice, each of the bands map to a part of the free energy parabola. So this first part is this part. And the next band here, so this part here, this now, you have to unfold this to get the free energy parabola here, okay? And so if you populate the lowest band only, then we will populate this part here. You can actually see this in pictures. This is the first Brillouin zone corresponding to the lowest band. These are the higher Brillouin zone corresponding to the higher bands. And if you do this, then we see like we create a box of atoms, essentially, in time of flight. We take these pictures, it looks like a box from all sides, okay? Because we've equally populated the lowest energy band. Okay, so this just to illustrate a little bit about the lattice. You can also populate higher bands. You see this here with the higher below zones. Okay, so with this, I want to show you a little bit about the band structure, and weakly interacting gases in optical lattices. Before we get into strongly correlated gases, let me show you a little bit about a recent tool that we developed. Wouldn't it be nice if we could really see individual atoms on individual lattice sites? And we can do that now with, we call it the quantum gas microscope. We've built a microscope where we create an optical lattice, not just in the middle of a vacuum chamber, but actually 10 micron away from a superpolished glass surface here. And this is then in the focus of a very high resolution microscope objective. By using fairly fancy laser cooling like Bill was telling you about, we can actually now image the individual particles. So let me show you a little bit how this works. So normally you cannot resolve individual lattice sites. Why is that? Well, because we only have a small aperture. Right? These lattices are created by light with k vectors that are counterpropagating. So the spacing is very small, only half a wavelength. Okay. But for imaging, we only have a small aperture, so we cannot possibly resolve these small distances. That's why we started to build a system that's very different. Here we have an effective, very large aperture because we have a large aperture lens already outside our vacuum chamber. And then in addition, we have a hemisphere in the vacuum chamber. So in the end, we can image a numerical aperture that corresponds to a light cone covering all these angles. So we now have a very high optical resolution. And we not only use this to read out, but also to create the optical lattices now. So, which gives us a lot of versatility. So here's a sketch again of, so we have only one 2D plane. By only one 2D plane, well, the depth of focus is very small, right, for imaging. So we start with one plane. And then this hemisphere, and it's just a movie, so you can see all the individual atoms. So here's a picture of the real apparatus. This is a glass cell where inside you have this very big vacuum. That's quite challenging by itself. These are the best vacuums you can make without cryogenic cooling. And then you have this little hemisphere inside and so on. This looks still pretty simple. The real experiment, of course, was more like this. So we're going to be fooled in the middle of all of this big glass cell. Yeah, and what we then do is that we start with the Bose-Einstein condensate in the magneto-optical in a magnetic trap. Mm-hmm.
Was there a reason why there were so few atoms in the center?
Yeah, I'll get back to that. So here's a cloud in a magnetic trap, and then we shine a single laser beam here at a very, very shallow angle that reflects, that creates a potential like this. And if you change this angle, we create a much lattice with a much shorter wavelength. This is not the lattice in the z direction here, which creates a pancake. Does that make sense? If you don't do anything but shine light like this, you get a pattern like this. And so our BDC smears out into a pancake parallel to our glass surface. Once we have this pancake, we want to have an optical lattice. And here, in contrast to other experiments, we actually project this through our microscope with very high resolution by using a mask.
How do you make it a single layer?
With exactly what I said here. We start with a lattice that is where the whole BDC fits into a single layer, and then we reduce the period, and so all the atoms end up in a single layer. Yeah, and then we shine light on, and we project a two-dimensional optical lattice. And the idea is now, because we use the same lens for making the lattice, we automatically have enough resolution to also image individual lattice sites. Okay? And so that's what we tried. There's one challenge. What happens if you have an atom on a single lattice site, and now you shine light onto the atom to do fluorescent imaging, let's say? What do you think happens? It scatters photons. These photons you could collect for telling whether there's an atom or not. Or what happens as well? Right, you would heat it up. Because the scattered light will impose momentum onto the atom so that it will climb up the ladder in the lattice. So to make sure that we can scatter a lot of atoms, we actually can make this lattice much deeper than when we do the many-body physics. So first we do the many-body physics in a fairly shallow lattice, then we increase the lattice depth by a factor of 1,000 and use laser cooling to make sure that the atoms stay on their lattice side. And that's kind of, actually, that's quite amazing that it's possible. I didn't actually expect that to work. It's another example, like what Bill Phillips said earlier. I mean, you shouldn't do an experiment that's really stupid, but even if you think it might not work all the way, often there are positive surprises. I was planning to use some kind of inhibition of light scattering to detect Mott states, I didn't really expect that it could really scatter a lot of photons from an atom on a single lattice side. But it turns out that briefly after, David Weiss showed in a much larger optical lattice that is possible. And so then we realized that even in this very small lattice side, it's possible to implement this Sisyphus cooling scheme that Bill was talking about to cool an atom on a single lattice side. I should maybe mention, because this is not really written in literature, how to think about this. In my experience, I know what you think, Bill, but you can never really understand laser cooling. Because often you're in between kind of different regimes where it's not clearly one way or the other. But I think what comes closest to what's happening on the lattice sides is, imagine an atom had two spin states, up and down. There are a few more spin states, but let's say an atom has two spin states. You can now create a situation by applying some nearly tuned light with some polarization gradient. Again, Bill was telling you about how this works if you have cross polarizations. With a polarization gradient, what then effectively happens is that the trapping potential is slightly dislocated between the two spin states. So you have one trapping potential like this. This is impressive. You have one like this. And it's here. So this is one lattice side. The potential for the two spin states for up and for spin down are a bit dislocated. It now so happens that if you're on the left, it's more likely that the atom gets pumped into this state. If you're on the right, symmetrically, otherwise it doesn't make sense. If you are on the right, then it's more likely that the atom gets pumped into a state that has a minimum here. So, let's say you're in the down state, and you climb up this wall here. Now it's likely that the atom gets pumped into the other spin state, but that's the state at the bottom of the oscillator. So now it's here again, scatters photons, might get hotter. Eventually, it's in the up state now, eventually it tends to get pumped into the down state again, but that's particularly the case when it's on this side. And so, Sisyphus it gets down again here where that potential is low. So if it's on the left, it gets pumped here, close to the bottom of the potential well, and vice versa. So that way we can actually reach that even though the atom scatters a lot of photons, gets heated like crazy, the net effect is a cooling, and we can scatter a lot of photons. We can just keep it on the same lattice side forever as we scatter light. That's great because the light is scattered. We can now take a picture of the atoms. So let's see how this looks. So we image this, then it will be split around the camera. And this is how it looks. So these are about 10,000 atoms in the optical lattice. You can clearly see them. Wait one second. You can clearly see the individual atoms here. If you zoom in, you can see the underlying lattice structure. You can see all these. And you can clearly tell by eye on each lattice side whether there's an atom or not, because you can scatter a lot of photons. The atoms never leave, essentially. So not by the lines. And so this is great because now we know, think about this, we have 10,000 atoms, we know the spin state of all of them through preparation, we know all of them were initially at the, in the ground state of the vibrational potential, because they were all in the lowest band, you could prove that, and we know the position of all of them. So we know everything essentially. So that's a big step compared to what you otherwise know about the quantum system. There was a question?
Sorry, why did the spin states get a split like that in the lattice site?
Because you create an effective magnetic field gradient. The polarization gradient with the tuned light corresponds to an effective magnetic field gradient. And so once it gets pulled to one side, the other to the other. If you have a harmonic oscillator, the gradient corresponds to a displaced harmonic oscillator. Right? Mm-hmm.
So there really is just one lattice site in each of the rolling dots, or cycling atom for each of those?
Yes, so I'll come back to that in a moment, but everywhere where you see bright, there is now, as you image, one atom. Yes. There's actually, if there are two, they disappear, but I'll come back to that.
Fluorescence so much brighter than others.
There's some overall, there's only some overall envelope here corresponding to the shape of the laser beams we use to cool the atoms.
When you use the fluorescence for imaging, does that process kind of disturb the phases at each site?
Yes, it disturbs everything. It localizes the atom, so it's one, and we'll come back to that later. Once you know where the atom is, there's no phase anymore. So that's yeah, so that's an interesting question actually. One question is, one could use this imaging in a way. So okay, here at the end of the day, the atoms do not end up in the vibrational ground state anymore. So we have destroyed our system. You could do the imaging with Raman cycling cooling, and we actually tried this in our second experiment now with lithium. And then you would end up in the lowest state again, and then you could again use this as a starting point for new quantum experiments. That's an interesting possibility. But your phase is lost, exactly. We'll come back to that.
This picture is taken after the fact, after you increase the depth
Yeah.
of the well,
Exactly.
100-fold.
Exactly. So we first do the many-body physics in a weak lattice, then we switch off all the tunneling, like we freeze time essentially. There's no time evolution anymore, and we take a picture. Yeah, this is just to mention, if you actually, so if you have two atoms on the side, what happens is, if you excite them into the excited state, you get into a molecular branch here. The atom, two atoms in the box, there's 1 over atoms 6, in the excited state 1 over atoms 3 in the tail here. And if you put an atom up here, this corresponds to the excited molecular state, and so the atom gets strongly accelerated. Depending on the tuning, this can be repulsive or attractive. But the net effect is that once you do this, the atoms gain so much kinetic energy, they immediately fly out of the lattice. So whenever you have two, they're gone. Turns out, what's not as trivial, but we'll see later that that happens. If you have 3 atoms, then 2 disappear and you have 1 again. So what we image is the parity of the atom number. And we have recently developed tricks actually so that we can really count the atoms in a binary way. The students actually work on it right now. So we can now count the atoms and distinguish whether we 0, 1, 2, 3 atoms. But for everything I will tell you about here, we do a parity detection.
So is this why some of the lattice sites were empty?
That's one reason why some of the effects were empty. That's why, yeah. But also what I showed you before was the thermal cloud. So there was just random at number 7.
So after you make the straps deeper, how long can you maintain the phase coherence?
So you make the lattice deeper by changing the detuning of the light. You use a different laser at much lower detuning. That automatically also starts quite a bit of heating. So the coherence is lost quickly, but we don't care about that time. In other experiments, they just bought the strongest lasers you can buy and just use the brute force method with a lot of power. That would be the experiment by Stefan Kuhr and Immanuel Bloch in Munich, which is the second experiment that can do this kind of imaging. Yep. Oh, I'm running on reserve battery power, it tells me. Sorry for that. It's kind of needs to tell me. Let's see. I think it's done. Why don't we reboot this thing with that? It's a mix of very old slides of mine, the new slides, and movies, and that pushes the capabilities of PowerPoint further. No. This. Okay. Yeah, of course it does. Because that movie doesn't like. Sorry, before it was working. So. Right, I wanted to show you some movies. You can even see I was hopping around in the lattice. Some of these movies, I didn't like this. Yeah. But the next thing I want to be talking about is, okay, so how can we use this as a tool now, and what's the kind of physics that we want to study? What's the kind of physics you get if you now load the atoms into the optical lattices? Before I want to go into detail, this is also like a quantum optics flavor kind of summer school, let me quickly talk about coherent states actually, because that's very helpful to understand superfluid-Mott transition. That's a very intuitive picture you can get, and learned last night. Some students told me that they hadn't really covered that. So let me go through it real quickly, and if you've never heard about it, it might be a bit too quick, but let me know. And if you don't know about coherent states or and the application of them in the context of light, what Glauber actually invented, then we give you as a homework until the next lecture. Please learn about that because it's super important and you can do so much with it. It's really, truly amazing because it plays a role in everywhere in quantum optics and also condensed matter. You can understand a lot of that in this context. We'll see.
So you said your lattice potentials are created with like a holographic plate.
Mm-hmm.
So have you experimented with things other than square lattices? Like, since I guess you kind of have like free reign over lattice design, 3D lattice design.
1 second.
Sure.
So how do you only do square lattice actually? And really not now because all 5 slides that I just added about coherent states are gone.
So maybe it's a good time to take a 5-minute break and see.
But I think I can not. I think we're quick. Okay. Yes.
Because we can take a quick break, 5 minutes, to stretch our legs and come back. How does that sound?
Okay, first break. 5-minute break.
Yeah. All right.
I'm sorry.
No, that's perfectly fine. I think we need to stretch our legs.